During the last lecture, we have learned general information about X-rays, electromagnetic spectrum, and also some historical steps in X-ray science and X-ray technologies. And today we will discuss the production of X-rays. There are many methods to produce X-rays, but why we use many methods to produce X-rays? The main aim, main target is that we would like to produce more X-rays. Okay, we would like to get high intensity X-ray sources. For this reason, we have many X-ray sources. I will explain step by step within this lecture. Let me start with the X-ray tube. During the last lecture, we have discussed all the details related to the X-ray tube. So what is the cathode material? What is the hot filament? What is the anode material? What is the glass envelope here? And water cooling system, modern X-ray tubes, and also high voltage sources. We have also discussed characteristic X-rays. We have discussed continuous spectrum, Bremsstrahlung, okay? We have learned all these things during the last lecture. For this reason, today I will not go into detail. So this tube is called as Coolidge X-ray tube, more or less the principal design of modern X-ray tubes. So discovered by William Coolidge in 1913, an American physicist. But there are also Crookes tubes, old ones. For example, let's have a look. This one, this is the X-ray tube. You can see it here. The design is more the same, but the older one. This is used in 1896 in Istanbul. Okay, very old one. Today, in the X-ray machines, for example, this is Rigako Smartlap X-ray diffraction machine, which we also have one in our laboratory in physics department. So here we have X-ray source, but you cannot see any tube like this. Okay, you cannot see the tube here. The tube is located within this shieldings, and here you can see water cooling and also the power supply cables. Another important X-ray source and generally used for scientific purposes in research centers, rotating anode tube. As I told you at the beginning of my talk, the main reason to produce different X-ray tubes is to get high intensities, more X-rays. Here, let me write the intensity in general form, okay? Photons per second per square centimeter. Okay, here you have an area. Let's say the area is 1 square centimeter. And how many X-rays are passing through this 1 square centimeter area within 1 second, let's say, okay? This is the general definition of intensity. Of course, there are also more complicated intensity definitions in X-ray books, but this is very helpful for the students. Photons per second per square centimeter. So how many X-rays, how many photons do you produce? This is the intensity. And here we have rotating anode tube. So what is the working principle of rotating anode tube? And what is the difference between this X-ray tube and rotating anode tube? So the general mechanism is same. Here we have a cathode material, and here we have a filament. You produce electrons. And then here we have an anode material. So we apply high voltage between cathode and anode. Then you accelerate electrons from cathode to the anode material, and then you produce X-rays. Here we have exit window, and here we have X-rays. Both continuous spectrum and characteristic X-rays are produced. But what is the difference between conventional X-ray tube and rotating anode tube? You can understand from the name, the anode material here is rotating during the production of X-rays. Why we are rotating the anode? As I explained during the last lecture, since electrons are accelerated to the very high energies under very high voltages between cathode and anode. We are talking about kilovolt, 30 kilovolt, 35 kilovolt, something like this. So these electrons are very energetic. And when they hit to the anode material, this anode material becomes very hot. So some part of electron energies is transferred to the anode material as a heat, okay? And this anode becomes very hot. But if you rotate this anode material, so each time electron will hit a fresh anode material, then you can decrease somehow the heating effects. In addition to that, each time electrons will hit a fresh anode area, then you can produce more X-rays, okay? The main reason is to produce more X-ray intensity, more photons. So then this does its job. Here we have a rotor to rotate this anode material, okay? And here there's a stator of the induction motor, and this is the glass envelope, and there's a vacuum inside. So the main mechanism is same as we have discussed for the X-ray tube during the last lecture. Do you have any question here related to the rotating anode tube? Okay, then let me show you a real picture of rotating anode tube. What do you see here? This is the cathode. Here we have an electron source, okay? Electron beam is produced here. Then this is the anode material, and this anode material is rotated by using a rotor here. And then electrons hit to the surface of the anode material, and then X-rays are produced. So the total size of the tube is around 25 centimeters, something like this. This is also the case for the X-ray tube. Look at this one. It is more or less the size of human head, let's say, okay? Now, let me show you a real rotating anode tube in a real machine. This is the X-ray source from Rigako company, a Japanese company, very expert on production of X-rays and also for the X-ray diffraction devices. So what do you see here? Here, there is an rotating anode tube. It is completely covered with radiation shielding, and here there is an exit window. What is exit window? Where X-rays can go out, okay? You can see exit window here. Maybe I should magnify. Here there is an exit window, okay? Here there are cables, power cables for the high voltage and also water cooling, you can see. And here we have high voltage sources and also water cooling system, let's say chiller, and also control unit. This is fixed rotating anode tube. It is not moving, but in conventional Neve X-ray diffractometers, what do you see here? Again, this is rotating anode tube, and here you can see water cooling and electricity cable coming from the high voltage source. So what do you see here? Again, this rotating anode tube is covered with lead for the radiation protection. And here, what do you see? Here we have an exit window, and then produced X-rays can go out from this window, and here you can put your material under investigation, and here there is an X-ray detector, which we will discuss later on. So this rotating anode tube is fixed, and this one is on the goniometer. You can move this rotating anode tube by using the computer programs, okay? You send command, just move this one to this angle, okay? So it can be moved by using the computer-controlled goniometer. Do you have any question here related to the rotating anode tube?
No, it's clear.
Okay, then let me continue with another type of X-ray source, which is called as Cyclotron Accelerator. The name comes from the cycle, okay? This is invented by Ernest Lawrence in 1929 or 1930. And he patented his discovery in 1932, and then he was awarded by Nobel Prize in 1939, Nobel Prize in Physics. Do we still use these cyclotron accelerators for X-ray production? Not exactly. This type of cyclotron accelerators today are mainly used for nuclear medicine to produce radioisotopes, okay, for medical purposes, especially for cancer treatment. And also this type of cyclotron accelerators are used to produce particle beams, accelerated protons. I will discuss the details here. So now let me discuss the principle of accelerator, how cyclotron accelerator works. Actually, we have two magnet poles. Let me draw. This is, let's say, half of the system. The system is like this. Let me draw here. This is the huge electromagnet. Do you know what is electromagnet? Electromagnet is, there are many cables here, many number of turns, and then you drive current and you can produce magnetic field, okay? If you change the direction of the current here, you can also change the magnetic field. So magnetic field is not here. Actually, magnetic field is here in the center, okay? So, and in the center of this, we have two Ds like this. We have a vacuum system, okay? This one here, these are shown by white color. So this is the electromagnet. This is the one pole of electromagnet. This is the another pole of the electromagnet. And here in between we have magnetic field, okay? And we have a vacuum chamber here. So let me discuss what we have within this vacuum chamber. Here I have shown magnetic field with H, but what do you see here? B. B is magnetic induction. And this is magnetic field. Generally in magnetism, B is written with H plus 4 pi m, okay? In vacuum, B is equal to H. This is just information from the magnetism, okay? So in some books you will see, or in some sources you will see, B is used for the magnetic field, but in some books, H is used for the magnetic field. But the actually magnetic field is this one. This is the magnetic induction. And only in vacuum condition, if there is no material, then this term will be 0. Then B will be equal to H in vacuum. So now let me delete this one and then discuss the mechanism of the cyclotron accelerator. Here we have one pole of the magnet, and here we have the second pole of the magnet, and we have magnetic field in between, okay? So then we will discuss why we need this magnetic field. Here we have two Ds with the shape of D letter, okay? Here we have two Ds, and all these things are under vacuum conditions. So here in the center, we have a proton source. Now let me ask you a question. How you can produce a proton source? I ask you to produce a proton beam, many protons, and how to produce protons. For example, at CERN in Europe, scientists are accelerating protons, right? And then collide them. So how do they produce protons? Proton is present in the nucleus of every atom, right? For example, let's consider hydrogen. Let me draw. Here, this is the hydrogen nucleus. And then this is the first Bohr orbit of the hydrogen. Actually, hydrogen has just one proton and one electron, right? If I remove this electron from the hydrogen atom, then I will have only a single proton. Then I have proton source. How to remove this electron from the hydrogen atom? As we have discussed during the last lecture, this electron has certain binding energy in this K shell of the hydrogen atom, okay? And if I send an electron to this atom with some certain energy higher than the binding energy of this electron, then I can take this electron from the hydrogen atom and then I can have pure proton, okay? By using this method, you can produce protons here. You can produce protons and you can have proton source in the center of this cyclotron accelerator. Do you have any question here?
Yes. Why we don't need the proton specifically? I mean, why we didn't take, for example, like electrons instead of the protons?
Good question. Actually, you can also accelerate electrons. For the synchrotron light sources, which we will discuss later on, we will use electrons to accelerate them to the high energies, okay? But in cyclotron sources, protons are used also for nuclear experiments. In order to produce radioisotopes, you need accelerated protons, okay? In order to produce radioisotopes, accelerated electrons will not help you. You need accelerated protons. So since devices are mainly used for nuclear physics experiments and for nuclear medicine, accelerating protons are preferred.
Okay, I got it. Thanks.
But the mechanism will be same if you accelerate electrons here, okay? I will discuss later on.
Okay.
So now let me continue. Here we have a proton source at the center of this cyclotron accelerator, and I would like to accelerate these protons. So how to accelerate protons? Proton is positively charged particle, right? If I apply electrical field, so let's consider that here we have a positively charged plate, here we have a negatively charged plate, and here we have a proton positively charged. Then you can accelerate this proton under the electrical field here, right? So if we have electrical field here, there will be a Lorentz force, which you have learned in the previous lectures, which is given by Q times E. E is the electrical field between these two plates, and Q is the charge of the proton, and this is the force acting on the proton due to the electrical field. Then this proton will gain kinetic energy. It will be accelerated, right? So how to produce electrical field here? Here we have an electrical field source, okay? Here we have an electrical field source. Let's consider that this is the initial position of the proton, and then I am accelerating this proton in this direction under the electrical field. So let's consider that within this area, we have electrical field. So I have accelerated this proton under the electrical field. Now proton has certain velocity, right? But I have here a magnetic field. So I know of another term in the Lorentz force, which is given by Q times V cross B. If the velocity of the charged particle is different from zero, there will be another force acting on the proton, right? So first force acting on the proton due to the electrical field here between the D's. And when proton has velocity, another force, second part of the Lorentz force, will act on the proton due to the magnetic field between the magnet poles here, right? So what about the direction of this force? This force, due to the electrical field, first part of the Lorentz force, will move the proton in this direction in a linear way. But this force, due to the magnetic field, will produce a circular way like this. Okay, so first motion due to the electrical field, this is the proton. This is linear motion due to the electrical field. And whenever it feels magnetic field, it will have this type of circular motion due to the second contribution to the Lorentz force. And then proton will follow this way. Let me choose another color of pen. And now it came back here. So if it enters into this area, it will feel backward electrical field and its velocity will be zero, right? Because electrical field is in this direction. So in order to further increase the velocity of the proton by using square wave source here, I change the direction of the electrical field here in this direction. Okay, now proton feels again a forward force. Okay, and then it will be further accelerated, and then due to the magnetic field, it will follow this way again. And here it will be accelerated again and follow this way. Whenever it enters here, it will be accelerated again and follow this way. And it will be accelerated here. Finally, it will reach very high energies, million electron volt, let's say, or mega electron volt. And then since the proton source has enough energy, it will go out from the system in order to use scientific or medical purposes. Okay, now we have very energetic proton source. So the direction of the electrical field, look at this one. Whenever proton enters here, the electrical field applies a forward force on the proton. And here again, electrical field applies a forward force on the proton. And for each time, we increase the velocity of the proton. So how do we do that? As I told you, we are using square wave source here. Square wave electric field accelerates charge at each gap crossing. Okay, but of course it can be adjusted very well. Otherwise, you can lose your velocity. You can lose the energies of the protons. So this is the main acceleration mechanism of proton source in a cyclotron accelerator. If you put here an electron, the mechanism will be same, but then electron will be accelerated in the opposite direction, since it will feel opposite force acting on the electron, okay? As I told you at the beginning of this transparency, within these two Ds, we have vacuum conditions, very nice vacuum conditions. If we wouldn't have vacuum here, very nice vacuum here, then these protons accelerated within this area may collide with the gas atoms, okay? And then they would lose their energies, okay? And this is unwanted situation. For this reason, the whole system is kept under good vacuum conditions. Do you have any question here?
No, clear.
Okay, then let me continue. This is picture of Cyclotron Accelerator. This is Proton Accelerator Center in Ankara within the campus of TAEK, Turkish Atomic Energy Agency. So what do you see here? Look at this yellow color. These are the magnet poles, these ones, okay? And here in the center, we have very nice vacuum conditions, and you produce proton source, and then you can use them for medical purposes, for nuclear experiments, okay? So whatever you want. So this is mainly used for medical purposes in order to produce radioisotopes. Do you have any question here? Okay, here, how to produce X-rays. We didn't discuss this one. We accelerated protons, but we are talking about X-ray sources. What about X-rays here? Where are the X-rays? What I have told you during the first lecture, an accelerated charged particle emits electromagnetic radiation. Let me clean all the things here. So here we produce protons, very energetic protons. But what about the X-rays? As I told you during the first lecture, if you have a charged particle, let's say proton or electron, and if they are accelerated, they will emit electromagnetic radiation during this accelerated behavior, okay? X-rays. So here, proton is accelerated. For the every acceleration case of proton, it will emit electromagnetic radiation. Actually, I have shown you a single proton here. Generally, we use proton beam, proton demeti. Okay, within the proton beam, we have many protons. Okay, so each of these protons will emit X-ray. So there will be many X-rays produced here in any direction. Okay, so you collect the accelerated protons from this exit, but X-rays can go everywhere. So if you open a window here, then you can collect X-rays, okay, and you can use these X-rays for your experiments. Now you have an X-ray source. Is it okay?
Yes.
Okay, good. Now let me continue. Here we have a synchrotron light source. Why do we need synchrotron light sources? Because we can get much higher intensities compared to the X-ray tubes. Let's say 10 to 20 times higher X-ray intensities can be produced by using the synchrotron light sources. So what is the meaning of high intensity? If you have more photons, you can carry out your experiment in a very shorter time, and you can get much more information compared to the X-ray tubes, okay? For this reason, synchrotron light sources are very important for scientific purposes and also for industrial applications. And there are many of them in the world. I will show you later on. So what is the working principle of synchrotron light source? And please remind me that I will also explain the meaning of physical meaning of synchrotron, why synchrotron name is preferred. So let me start with the electron gun. We need a particle source. Okay, here you can use electron source. In some synchrotron sources, people use protons, okay? But mainly synchrotron light sources use electrons as charged particles. Here we have electron source, we produce electrons, and then we accelerate electrons in a linear stage here. This is called as microtron. And within this linear stage, we have Linux, linear accelerators. I will go into detail in the forthcoming transparencies. Within the microtron, electrons are accelerated up to energies of MeVs. Let me draw here, energies up to MeVs, okay? In the linear stage. Then here we have a circular stage, which is called as Synchrotron Accelerator. So these electrons are coming from the electron gun, are accelerated up to MeV energies, and then they are injected into the Synchrotron Accelerator, okay, this small ring here, and they are accelerated within this ring up to very high energies, giga-electron volt, okay? Let me also write this one, let's say around generally 3 giga-electron volt, okay? So we injected electrons with the energies of MeVs into this Synchrotron Accelerator, and then we continue to accelerate them up to the energies of giga-electron volts. Now we have very energetic electrons, and their speed is close to the speed of light, okay? And then when they reach to the enough energies, we inject them into the bigger ring here, which is called as storage ring, okay? This is the storage ring. So first of all, electrons are produced here. They are accelerated in the linear stage and then injected into the Synchrotron Accelerator. And then they reach to the giga-electron volt energies, and then they are injected into the storage ring. So you can understand from the name storage, you store electrons here. You store very high energetic electrons here for a long time. So they are traveling here. What about X-rays? Of course, during the acceleration, okay, you produce many X-rays here due to the very energetic electrons. If a charged particle is accelerated, it will emit electromagnetic radiation. So due to that rule, you will have many X-rays here in this Synchrotron Accelerator part, but we are not dealing with this X-rays. We will get much more high intensities by using the undulators, wigglers. Here, I will go into detail. So here, we mainly accelerate electrons and store them here, okay? So, of course, all the system Synchrotron Accelerator, and also this storage ring are under UHV conditions, high vacuum conditions, okay? Maybe I should mention here, another name of Synchrotron Accelerator is booster. Actually, this name is more common. So the name of this ring here, booster, Synchrotron Accelerator, is called as booster because electrons injected into this booster with MeV energies, and we boost their energies, we increase their energies up to giga electron volt. For this reason, the name is booster. So here, electrons are traveling, okay, for many hours without losing their energies, let's say. Of course, in reality, they lose their energies and you have to inject new fresh electrons. I will go into detail about this. And here we have an undulator. I will talk about the working principle of these undulators in the forthcoming transparencies. And here within the undulator, X-rays are produced. Here we have electron beam, and here within the undulator, we produce X-rays. Now, starting from the undulator, we have X-rays, okay? Instead of undulator, bending magnet and also wigglers are also used. I will go into detail. And here we have X-rays. So within the beamline, you can adjust, you can manipulate the energies of the X-rays by using monochromators. And here there's a beamline, and here we have end station. You can use X-rays, produce X-rays for your experiments, for scientific purposes, for industrial purposes, for technological applications, okay? Whatever you want, there is an end station here, and you use X-rays. So what is the difference compared to the X-ray tube? The size of an X-ray tube, very small, right? Size of rotating on a tube, very small, 20 centimeter, 25 centimeters, something like this. And what about the size of the synchrotron light source? The diameter of this storage ring is around 100 meter. Okay, I will show you pictures. Huge facilities in order to produce very high intensity X-rays, and they are very, very useful. Do you have any question here?
No.
Okay, then let me continue. Here you see a synchrotron light source in United States. The name is NSLS, National Synchrotron Light Source. Here you see booster part, and the bigger ring is the storage ring, and there are many beam lines here. So actually here I have shown you just single beam line, but in reality, synchrotron light source has many beam lines. So you can take another beam line here, another beam line here, another beam line here. So same mechanisms are included here, okay? And another beam line here, another beam line here. Sometimes you can split these beam lines into 2 or 3 parts by using the optical methods, okay? So here we have one end station, another end station, and another end station. So 8 hours X-rays are coming to this end station, and then direct them into this end station for another 8 hours, and then you direct them to this end station for another 8 hours. So if you are carrying out measurement here, you cannot use X-rays in these 2 beam lines, okay? But if you have a single beam line, and if you have enough energetic electrons in the storage ring, you can use this beam line for 24 hours for many days. So these machines are working 24 hours, 7 days usually, and they have some commissioning days or commissioning weeks per year, let's say 2 weeks, something like this. They repair something or upgrade some hardware or software, and then they start again working for 24 hours, 7 days. Let me continue to show you pictures of the synchrotron light sources in the world. So here you see storage ring, bigger ring, and beam lines, okay? So these are the facilities for the users, library, let's say, sometimes restaurant, and also administrative centers, something like this. And here there are cars. You can see the size of the facility. Okay, the radius is more than 100 meters. And this is the Petra tree at Daisy in Germany, which is Electron and Synchrotron Laboratory, okay, in Hamburg. And the name of this synchrotron light source is Petra 3, and there are many beam lines here. This is huge experimental station area, okay, and there are many beam lines here in the Petra 3 building. So now let me show you another picture from the Spain. This is the ALBA synchrotron light source. It is active. They are using synchrotron light source. And here you can see, you can imagine this is the booster and this is the storage ring. Look at this one. This is the booster, this is the storage ring and experimental stations, okay, beam lines. This is the diamond in England. So you can easily see booster. This is the probably LINEC, microtron, electron source, microtron and booster, and then storage ring and beam lines. So again, you can see the size of cars, huge building. I don't know the radius of this building, so you can check from internet. And there are many synchrotron light sources in the world. Here you will see different colors. You see, for example, here there is a yellow color, and this is violet, this is green, this is red, and red, green, and violet, and yellow colors. There are different colors. So what are the meaning of these colors? If there is yellow color, it means that planned or under construction. For example, here, Sesame, located in Jordan. So it is more or less finished, but some parts are still under construction. Alba is finished in Spain. I have shown you the picture. So Kendall is planned, but it is not under construction. I think it is canceled as much as I know. And here you see green color. This shows us second generation synchrotron light sources. There are many green colors here in the United States. NSLS, I have shown the picture, CHESS and SRC here, and also CAMT here, and also in Europe, Delta, Anka, Delta in Dortmund, and also ELSA here, and DELSI, Kiev, KIPT, okay, and also here, and this side. So in Japan, there are many photon factory, okay, so many of them, so also in Australia. So now let me show you the third generation synchrotron light sources. This was the second generation, this is third generation. I will discuss what is the difference between third generation and second generation. So here, Canadian light source, advanced light source, and SSRL, and what else? APS, advanced photon source in United States, and BESSY is now third generation. So MaxLab, as much as I remember in Sweden, I have shown you Diamond in England, it is also third generation. Soleil in France, third generation. And this is a Civis light source. ESRF in Grenoble, European Synchrotron Radiation Facility, it is also third generation. Elettra in Italy, and Spring 8 in Japan, third generation, okay? So there are many third generation synchrotron light sources, and this violet color shows us free electron laser, another type of X-ray source. I will spend some more transparencies related to this free electron laser, but now I just would like to show you here Jefferson Lab FEL, Duke FEL here in the United States, and VU FEL, and here European X FEL at Daisy in Hamburg, and also what else here, IR-FEL in Japan, okay? There are also many FEL facilities in the world. So what do you see here? You see many second generation, third generation synchrotron light sources and also FELs in North America, let's say in the United States and also in Canada. Here in Europe, you also see many second generation, third generation and synchrotron light sources and also FEL, also in Ukraine and Russia, and also in, let's say, China and in Japan, you see many light sources. So now let me discuss the importance of this synchrotron radiation sources or FEL sources. So if you are dealing with science, then you can produce the products, you can get many patents, and then you can be very powerful in economically and also politically and also in defense industry. Let me give you some examples. Let's consider that we are talking about cars, okay? So what are the main car manufacturer countries? United States, Europe, South Korea, Japan, and also China, okay? So main car manufacturers are located here. So now let me also continue with the mobile phones, smartphones, okay? iPhone developed here. So what about Samsung in South Korea? Sony, for example. And here, Nokia, okay, in North Europe, and also many other companies related to the mobile technologies. And now let me give you another example. Who can produce rockets to reach space? China, Russia, United States, okay? So if you are dealing with science, then you can get very nice products and you can be very strong economically. And look at this area. You can see more or less no synchrotron light source in this area, in the Balkans here, in the East Europe, and also in Turkey, in Middle East, okay, there is nothing here. In Iran, here, there is nothing. And also look at the Africa. Nothing in North Africa, in Sub-Saharan Africa, in the South Africa, there is nothing, okay? So actually, these countries are known as poor countries and they are not producing high technologies, okay? But some of these countries, for example, Saudi Arabia here, and also some North Africa countries, they are petroleum-rich countries. And they can produce this type of instruments, okay, in order to improve their science and technology in the countries. But unfortunately, we cannot see any synchrotron light source or FEL in these countries. Here you see Sesame. So in Sesame, in Jordan, there is a synchrotron light source. Actually, they got main parts from the Germany, from the old Bessie instrument in Berlin, and then they developed it. Now I think, as much as I remember, it is third generation synchrotron light source, and now they have first X-ray beam, I think 2 or 3 years ago, and now they are building the beam lines. So this is a UNESCO project. So partners are the Jordan, Turkey, Israel, Iran, as much as I remember, Pakistan, and also Egypt. So these are the partners. So if you are not dealing with science, then you have to buy important products, important technologies from the producing countries. Okay, now China is becoming leader in science. They have much more publications compared to the United States. Even in nanotechnology, for example, they have more publications during the last 5 years. So now they are becoming economical leader in the world. If you are dealing with science, if you spend money, if you spend time for the science, then it helps you to be strong economically. So then let me continue. Do you have any question?
No.
Okay. Now let me show you a picture of the Turkish Accelerator Center. This is planned in Ankara. It's in this Turkish Accelerator Center. A synchrotron light source is planned, and also an infrared FEL is under construction, but it is not finished. And also some other light sources are planned, but this is not started, okay, just proposed. But this is under construction, this infrared FEL. So now let's discuss each part of the synchrotron light source. So here we have electron gun. I will not go into detail. Here we have a microtron, a linear stage. There are linear accelerators here, which is shortly called as LINAC, okay, linear accelerator. And then here we have a synchrotron accelerator part. I will also explain what is the meaning of synchrotron, okay? What is the competition between electric field and magnetic field? within the booster. And also I will talk about storage ring, how to keep the electrons in this circular orbit. And then I will talk about the production of X-rays within the insertion devices like undulators or wigglers and also bending magnets. Then I will explain the principles of the monochromators. I will explain what are the important things within the beamline, and we will finish with the end station of the synchrotron light source. Now let me continue with the LINAC. Here, this is the picture of LINAC, this one here, from the Australian synchrotron. This type of LINACs contains RF cavities, cavity, boşluk, oyuk, kovuk. The design of the tube is completely different from a standard tube, okay? It has some certain features in order to apply RF frequencies in order to accelerate the charge particles within the LINACs. So here, this is the main working principle of a RF cavity. Let's say we have an electron here, and then this is the LINAC. Actually, it looks like this. This is the first part of the RF cavity, second part, third part, fourth part, okay? And we apply voltage oscillates with a radio frequency of 1.3 gigahertz for this example, or 1.3 billion times per second. So you change the polarity here, okay, by using the RF source. So electron enters here, and within the RF cavity, we have force acting on the electron to move it forward, okay? We have electrical field here. But if the force in the forward direction here within that cavity, in the neighboring cavity, it is opposite. And here, again, forward, here, backward, okay? So when the electron enters into the first cavity, it feels force in the forward direction and it is accelerated. We accelerate the electron. But whenever it enters into the second cavity, you have to reverse the direction of the force acting on the electron along the forward direction, right? So how to do that? It has been done by using the RF sources, okay? We have a voltage generator, RF voltage generator, and then whenever electron enters into the second part, it feels again a force in the forward direction. Again, when electron enters into the third cavity, it feels force in forward direction. So then the electrons always feel a force in the forward direction. So let me draw something here. There is a force acting on the electron in this direction, but here we have opposite. Since we are using an RF voltage source, whenever this electron or electron beam enters into the second one, again we reverse the force and it becomes like this here. So in the first case, electron feels a forward force here, but here we have a backward direction. So whenever electron enters into the second one, we change the direction of the force here by using the RF voltage generator. Then it will be like this. If the force acting on the electron is in the forward direction here, then it will be backwards. Okay, here backward and forward here. So when the electron enters into the third part, what do you see here? Backward. Then change it to the forward. If I change it to the forward, then this will be backward, this will be forward, this will be backward. When electron enters into the last cavity, then I change the voltage source to provide a force acting along the forward direction. Then this will be backward, this will be forward, this will be backward. Okay, so whenever electron enters into the second place, third place, fourth place, you play with the voltage generator, which induces an electric field inside the RF cavity. Okay, this has been done in very fast way. We are talking about 1.3 billion times per second. Okay, you change the direction of the forces within the cavities which acting on the electron. So with this method, electron feels always forward force and then accelerated within each cavity. Finally, we have electron beam here, and it is very energetic. It reaches to the energies mega electron volt. Here, there is an animation from Wikipedia. So what do you see here? This animation is prepared for the proton source. Proton sources used in CERN, for example, in order to accelerate protons, but the mechanism of the LINAC and RF cavity is same. Here you have a positively charged particles, and then here you have a voltage source. What do you see here? Proton is positively charged particle, and this must be positive. And here we have negative sign, and proton is accelerated. Whenever proton beam comes to this second cavity, this becomes negative and this becomes positive, and then it is accelerated again. Whenever it comes here, this becomes positive, this becomes negative. Proton beam is accelerated again. Finally, proton beam has huge energies. Okay, it is same also for the electron. If you have electron beam here at the beginning, it must be negatively charged. This is positively charged. Then electron beam is accelerated from the source to this direction, in forward direction. And whenever electron leaves from the first part, this becomes negatively charged, this becomes positively charged, let's say, okay? And then you accelerate electron again, you accelerate electron in each part of the RF cavity. Finally, electrons have huge energies. So this was the working principle of RF cavity. Here you see a real picture of a RF cavity. So these are very expensive devices, tools, especially superconducting RF cavities are very expensive. We are talking about $1 million for just 1 meter or 2 meter RF cavities. And this must be designed very well, okay? And production of this RF cavities must be done also very carefully. Otherwise, the real situation will be completely different from your design. Do you have any question related to the LINAC?
No.
Let me continue with the booster. So LINAC is linear accelerator. You see linear, you accelerate electrons up to mega electron volt energies, and then we inject these electrons into the synchrotron accelerator. So in the synchrotron accelerator or in the booster, we keep electrons in a circular orbit. How to keep electrons in a circular orbit? In order to keep the electrons in circular orbit, you need magnets, right? So here you accelerate electron and here you have a magnet. Here you accelerate electron and here you have a magnet. Okay, many magnets in the booster. These are the magnets. I will show you the real pictures of the magnets used in the booster in synchrotron light sources. So by using these magnets, electrons are kept in a circular orbit by using the Lorentz force. Okay, electrons are accelerated, they have certain velocity. By using the magnets, we apply a magnetic field, and electrons have certain charge, then a Lorentz force acting on the electrons, and then we can keep them in a circular orbit. So how to accelerate electrons? In order to accelerate electrons, as I explained, we use the first part of the Lorentz force, electric field, and then charge of electron. Then we produce a force acting on the electron, then we accelerate electrons. So now, why the name is Synchrotron Accelerator? Here, let's consider that you have injected electrons from the microtron and they have energies around MeVs, and you have another LINAC, okay? And then you further increase the energy of the electron, and here you have a magnet. In order to keep this electron in this certain orbit, amount of magnetic field is very important. So here, if you further increase the electron between two magnets, the magnetic field here must be bigger than the magnetic field in the first case here, because velocity is increased. Then in order to keep the electron in the circular orbit, you have to increase the magnetic field also. Here you further increase the energy of the electron beam, and then you have to increase the magnetic field here, okay, in order to keep the electron in this circular orbit. So if you increase the velocity, you also have to increase the magnitude of the magnetic field. So since this has been done in a synchronized manner, you increase the energy, velocity, you increase the magnetic field, increase the energy, velocity, increase the magnetic field. So you have to do this one in a synchronized manner. For this reason, the name is synchrotron, okay? It comes from the adjustment of magnetic field and energies of the electrons in a synchronized manner. For this reason, it is called a synchrotron accelerator. Another name is booster, as I told you, because we boost the energies of the electrons to the high energies, such as 3 giga-electron-volt. So this is the booster. Of course, all the system is under UHV conditions, ultra-high vacuum conditions. Do you have any question here? Let me continue with the picture of Australian synchrotron light source. So what do you see here? This is the huge ring. This is the bending magnet, okay? You can see this one. So in order to keep the electrons in a circular orbit, you have to use these magnets. And here you see elderly people. They are traveling in the synchrotron light source. So why? What are they doing there? These are the taxpayers, okay? People pay taxes to the government, and then governments spend money for these purposes, and then they are checking what the scientists are doing here, where the money had gone. They are checking this one. So generally in synchrotron light sources, also for many other governmental facilities, there are open bays, okay? And taxpayers can visit and see what is happening inside. So then you can also motivate them with their studies on science and technology. So during this visiting days, the system is down, okay? It is not working. Otherwise, you produce X-rays here, and there's a radiation here, very dangerous for the people. Normal people can never enter into this area, okay? And since the machine is shut down, so they can visit and they can see what is happening. So now let me continue with the bending or dipole magnets. So as I told you here in the booster part, in order to keep the electrons in a circular orbit, we are using magnetic field. We are using magnets, okay, dipole magnets or bending magnets. We are also using magnets within this bigger ring, storage ring, okay, in order to keep again the electron beam in this circular orbit. So what is the bending magnet or dipole magnet? Dipole means two poles, okay? First pole, second pole, this is dipole magnet or bending magnet. Before the bending magnet and after the bending magnet with red color and green color here, there are focusing magnets in order to focus the electron beam, and then electron beam enters into the bending magnet and then goes out. So when the electron beam is passing through bending magnet, each electron emits electromagnetic radiation, okay? Since electrons have accelerated behavior here, as we have learned, if a charged particle is accelerated, it emits electromagnetic radiation. So within the electron beam, each electron emits electromagnetic radiation, and now we have synchrotron radiation, very bright, with very high intensity compared to the X-ray tubes. As I told you, the intensity compared to the X-ray tubes, conventional X-ray tubes, is 10 to 20 times higher compared to the conventional X-ray tubes. depending on the synchrotron design. So this is the N pole, this is the S pole, or it can be reversed. So you bend the electron beam and then keep the electron beam in a circular orbit, but also X-rays are produced here. So you accelerate electrons in a RF cavities, and then you keep the electrons in a circular orbit by using the bending magnets or dipole magnets. So within each magnet, since electrons have accelerated behavior, then you produce X-rays, okay? But we will not use X-rays within the booster. We will use X-rays produced in the insertion devices because intensity here is much bigger. Okay, now let me continue with the storage ring. What we have within the storage ring? Within the storage ring, again, we have bending magnets in order to keep the electrons in a circular orbit, and also we have UHV related issues, parts, pumps, okay? So this is also under good vacuum conditions, UHV conditions. We have bending magnets and insertion devices. Insertion device means that inserted device into the storage ring, okay? We have many of them. So here you may have another insertion device, another beamline, another insertion device, another beamline, another insertion device, another beamline, and generally conventional synchrotron light sources have between 10 and 20 beamlines, sometimes more, sometimes less, depending on the synchrotron light source. So there are many beamlines around this storage ring. So we accelerate electrons by using the microtron to the MEVs and then injected them to the synchrotron accelerator, to the booster. And within the booster, electrons are accelerated up to giga electron volts, 3 giga electron volt, for example. Then they are injected into the storage ring. And since we have UHV conditions here, we can store electrons for a long time while keeping their energies, okay? Although you have UHV conditions, electrons can lose their energies. And also, since they are deflected within the bending magnets and also in the insertion devices, they lose their energies by time. Then you have to inject new fresh electrons with some certain high giga electron volt energies from the booster to the storage ring. This is called as injection. So let me draw something here. Let's say this is the time axis in hour. This is the energy, let's say, or we can also use intensity. Let me use also intensity, then you can better understand. So at the beginning, you injected fresh electrons from the booster to the storage ring, and then by time it decreases. After 8 hours, it decreases, and then you have to inject fresh electrons from the booster again. So after 8 hours, it goes down again, okay? And then you inject fresh electrons. This injection time takes more or less 10-15 minutes, let's say, okay, as much as I remember from the BESSE 2 in Berlin. So during this injection time, you cannot carry out experiment, okay? So you have to stop your experiment because there will be no X-ray, and you will wait until the injection is ready. So the main disadvantage of this injection is that you have to stop your experiment for each 8 hours. Okay, you cannot carry out continuous experiment for 24 hours. You have to stop your experiment. And in addition to that, what do you see here? The intensity of X-rays. You are measuring something here at the end station, and you are taking a data, and at the background signal, you will see this decrease in your data. Okay, so you have to subtract this decrease in the intensity of the synchrotron light source, intensity of the incoming X-rays. Otherwise, you cannot analyze your data. Okay, this was in the second generation synchrotron light sources. But in the third generation synchrotron light sources, as I have mentioned in the previous transparencies, we have continuous injection or top-up injection. So what we have here, the energy of the electrons and intensity at the end station is kept more or less constant, okay? So without stopping your experiment and without decreasing the intensity of the X-rays, you can get this type of continuous behavior. So this is called as continuous injection or top-up injection. Third generation synchrotron light sources have this property compared to the second generation. Do you have any question here?
No, you may continue.
Okay, now let's discuss the insertion devices. Here in the storage ring, we have many insertion devices. Insertion devices can be undulator or wiggler. So what is undulator? What is wiggler? Let me start with the wiggler. Wigglers are the periodically arranged permanent magnets, okay, which is called as Holbach array, okay. Here you have permanent magnet with the magnetization in this direction, another permanent magnet with the magnetization in this direction, another permanent magnet with the magnetization in this direction. In the opposite side, again, we have permanent magnets, which are also aligned in the style of Holbach array. So here it has magnetization like this, it has magnetization like this. So you have many permanent magnets. So here we have electron source. Electron is a charged particle, negatively charged. Whenever it enters into this Holbach array, electron feels magnetic field, and then it is deflected due to the Lorentz force, which I have discussed, okay? So, which is given by QVB. Electron has certain charge, certain velocity, and here we have B, magnetic field. But what do you see here? The direction of the magnetic field within the Holbach array is changing, okay? So then electron has this type of movement, like a snake, okay? Like a movement of the snake. So then for each accelerated behavior, electron emits electromagnetic radiation, X-ray, in forward direction, okay? So here we have much better picture from the Spring 8 in Japan. So here we have electron beam, and then they enter into the Holbach array, into the wiggler, and then they have accelerated behavior and they emit electromagnetic radiation, so we can produce synchrotron light source, we can produce X-rays. These are the X-rays, okay? This is the wiggler, and undulator also has the same mechanism, but there is a difference between undulator and wiggler. There are also superconducting undulators. So the main difference is that undulators can produce more X-rays, more intensity, okay? Intensity of X-rays produced by undulator is much higher compared to the intensity of X-rays produced by the wiggler. Here you can see an undulator in the Spring 8. This is the FEL, X-ray free electron laser undulator, very long one. This is the undulator, and here in the center you send your electron beam, and the whole system is under vacuum conditions, okay? So this is the cross-sectional picture of, let's say, this undulator. Now let's compare the intensities of bending magnet, wiggler, and undulator. As I told you, in the synchrotron light sources in the storage ring, we have bending magnets to keep the electron in a circular orbit. We have undulators and we have wigglers. So within each device, we produce X-rays. So which one has better intensity? Of course, undulator has better intensity, much higher intensity than the wiggler, and wigglers have much higher intensity compared to the bending magnets. And this is the comparison between the intensities of different devices in the storage ring. Of course, depending on your application, depending on your needs, even bending magnets are very useful. Wiggler beamlines, undulator-based beamlines, so you can use any of them. And in modern synchrotron light sources, you can find beamlines with these different insertion devices and bending magnets. So now let me continue with the beamline. So within the undulator or within the wiggler or within the bending magnet here, you produce X-rays. Now we have X-ray beam, okay? we produce the X-rays. So then have to carry these X-rays to the end station. In order to carry the X-rays to the end station, we use beamline, in Turkish demet hattı. Okay, and here within the beamline, we have windows to watch the beamline, what is happening inside. There are slits to shape the X-ray beam, and there are focusing mirrors to focus the X-rays, and also there is monochromator. Okay, what is the monochromator? Mono means tek, single. Chroma comes from the color. Okay, single wavelength. So here, from the undulator, or from the wiggler, or from the bending magnet, X-rays are coming, and they have different wavelengths. And within these different wavelengths, I would like to choose a single monochromatic wavelength. Depending on your experiment, you can adjust the energy, you can adjust the wavelength of the incoming X-rays by using monochromators, and then you send them to the end station. So here we are talking about electrons. Electrons are produced, accelerated within the line X, accelerated within the booster, and then kept in the circular orbit by using the magnets. Again, here you use the magnets. And so in order to accelerate or change the direction of the electrons, we use electric field and magnetic field. But what about X-rays? How to direct X-rays? X-rays are electromagnetic radiation, photon. So by applying magnetic field or electric field, you cannot apply a force on the electromagnetic radiation because it has no charge. Okay? In order to feel Lorentz force, a particle should have a charge. But electromagnetic waves have no charge. So how to direct this, how to change the direction of the electromagnetic waves, how to collect them, how to focus them. So by using optics, okay, by using focusing mirrors, by using the reflectors. So by using optical methods, you can send your X-rays to the end station. So within the beamline, we are using the optic rules. So let me show you here what is the working principle of a monochromator. Then let me continue with the end station. Monochromator is a vacuum chamber. Let's consider that there is another undulator here. And this is a beamline. X-rays are produced within the undulator, and they are going into the monochromator, and then they will go to the end station. Okay, within the undulator, we have mirrors, perfect mirrors like this, 2 bonds or 4 bonds like this. So X-rays are coming and then reflected like this. So then they go to the end station, let's say. Okay, so here, what do you see? This is the incident angle here, and this has certain d value, interplanar distance. If you use the Bragg's law and lambda to the sinus theta. Theta is this one, this incident angle, and d is the interplanar distance depending on the mirror here you used. And then lambda is the wavelength. So this is fixed. Interplanar distance within this mirror is fixed. And if you manipulate the theta, then you can manipulate the wavelength. So what you do within the monochromator. Okay, so this is the working principle of monochromator. So then let me finish with end station, the synchrotron part. So this is the storage ring. Within the storage ring, electrons are traveling in a circular orbit. And here in the insertion device, undulator or wiggler or bending magnet, you produce X-rays. So starting from this one, you have X-rays, no electron. Electrons are going to travel in the circular orbit. Then here we have a monochromator. And then after monochromator, you collect them by using the focusing mirrors, and you focus them into your experimental station, and you focus them into your sample. Then these are the X-rays deflected from the, or reflected from the sample, and they go to the detector, okay? And by using the computer, you can get your data. Do you have any question here?
No.
Then final method to produce X-rays, free electron lasers. So within this free electron lasers, you can produce much higher intensity compared to the synchrotron light sources. And since you have very dense X-ray source here, you can also use this one for military applications. I will show you. So what is the working principle? This is the sketch from the Jefferson lab in the United States. So what we have here, electron source again, you accelerate electrons, and here there's a superconducting RF cavity, you accelerate electrons. And here there's a wiggler or undulator, okay? Then within these wigglers or undulators, but in FELs, in free electron lasers, there are very long undulators, very long wigglers. Why the name is called as laser? Maybe you remember from the optics or from the laser courses. For the lasing process, we have optical cavity mirrors here, and you produce X-rays. They are reflected from this mirror and then come back here, reflected here, and you produce many X-rays, and superposition of this many X-rays produces laser light, okay? Free electron laser. So this free electron laser has very bright intensity, and you can use it for many applications. This is the Turkish Accelerator Center in Ankara, and here within this building there is an infrared FEL. This is still under construction. Some parts are installed, and I think many parts are missing. They are still going on this. They are still constructing this infrared FEL. As I told you in the world map, there are many FELs, different FELs in United States, in Europe, also in Japan. So let me finish with this transparency. This is the FEL weapon. United States Army is working on this, and they succeeded a lot. So this is a warship, and then here there's a target. For example, there is a missile or there is an enemy plane, okay? So here there's a free electron laser. You send the laser beam. Within seconds, you can explode, you can hit this missile or enemy target by using the free electron laser. And compared to the conventional, for example, Tomahawk missiles, using free electron laser, you spend very less money, okay? For example, one Tomahawk missile, as much as I remember, costs $1 million. And one shot of free electron laser is around $1, okay? So very expensive. Of course, it has some disadvantages compared to the conventional missiles, but very useful. And the United States Army and also armies of some countries are working on this to use these free electron lasers to defend their military vehicles. And you can also find many videos on this issue on the internet. So with this transparency, I have finished the production of X-rays. We have seen X-ray tubes, we have seen rotating nanotube, we have seen cyclotron accelerators, we have seen synchrotron accelerators, and finally we have finished with free electron lasers. So each of them has advantages. For example, in X-ray tube, intensity is much smaller compared to the free electron lasers, compared to the synchrotron light sources, but X-ray tubes are very cheap, okay? You can use an X-ray machine in your laboratory, but in order to have a synchrotron light source, you have to spend more or less $0.5 billion, okay? And also maintenance cost huge per year. So each of them has advantages and disadvantages, but in order to have high intensities, you have to go to the synchrotron light sources and free electron lasers. And these instruments, these facilities are not only used for the scientific purposes, they are also used for industrial applications. If you visit the website of one of the synchrotron light sources in the world, you will see that many different applications from the industry and technology also applicable in synchrotron light sources. Any question?
No, thanks.
Okay, see you then. Bye-bye.